Pittsburgh, 1894. The Westinghouse plant floor where American industrial power was about to be decided by the weight of a motor. European-trained engineers stood confident around their 45-pound Siemens motor, precision-machined steel bearings, elegant efficiency that represented centuries of German engineering tradition. Across the factory floor, Frank Sprague's motor sat like a cast-iron monument, 85 pounds of what the Europeans dismissed as primitive American overbuilding. The German chief engineer held both motors, shaking his head at the crude American design. Bronze sleeve bearings where precision steel should be. Oversized frames that seemed to mock European sophistication. Factory conditions that would soon test both philosophies, coal dust, temperature swings from 20 degrees below zero to 120 above, 12-hour shifts with zero maintenance time. In European workshops, motors ran in controlled environments with daily care. In American factories, they had to survive industrial hell. The Europeans agreed to a 2,000-hour endurance test, certain their precision engineering would triumph over American brute force. But deep in those Pittsburgh steel mills, something about American over-engineering was about to prove the Europeans had been calculating for the wrong variables entirely. The morning shift bell at Westinghouse's East Pittsburgh plant clanged through the November air as Carl Steinmetz adjusted his wire-rimmed spectacles and opened his leather-bound logbook to a fresh page. The German engineer's precise handwriting documented every specification as he examined the two motors that would settle a debate consuming American industry. His Siemens motor represented 4 decades of German precision engineering, 45 pounds of carefully calculated efficiency, with steel bearings machined to 5/10,000ths of an inch tolerance. The commutator segments gleamed like jewelry, each copper bar fitted with mathematical exactness that German apprentices spent years learning to achieve. Across the testing floor, Frank Sprague's motor squatted like a mechanical bulldog. 85 pounds of cast iron and bronze that violated every principle Steinmetz had learned at the Technical University of Berlin. The American design seemed to mock European sophistication with its crude, oversized frame, bronze sleeve bearings that belonged in railroad equipment, and commutator built like armor plating. Steinmetz lifted both motors, feeling the stark difference. The Siemens unit balanced perfectly in his hands, every ounce serving a calculated purpose. Sprague's motor required 2 hands and felt like lifting a blacksmith's anvil. "Herr Sprague," Steinmetz said, his English careful but confident, "your motor weighs nearly twice our specification. In Germany, we calculate exact material requirements, no waste, no unnecessary mass." He opened his logbook, revealing pages of mathematical calculations. "Our motor achieves 1,200 RPM with 45 pounds total weight, efficiency through precision." Sprague studied the German's meticulous notes, recognizing the brilliant engineering behind every decision. The Naval Academy had taught him to respect mathematical excellence, and Steinmetz's calculations were flawless for laboratory conditions. But American factories weren't laboratories. "Your numbers are perfect, Carl, for perfect conditions." He gestured toward the factory floor beyond the testing room, where the constant rumble of machinery mixed with coal dust and steam. "But look around. Nothing here is perfect." Walter Manning emerged from the bearing workshop, wiping grease from hands that perpetually carried the smell of cutting oil. His father had maintained railroad engines for 30 years, teaching Walter that elegant engineering meant nothing if it couldn't survive the real world. "Carl, your precision bearings are beautiful, but what happens when coal dust gets in those 5/10,000ths clearances? What happens when temperature swings 40 degrees in one shift?" Steinmetz consulted his specifications. German factories maintain clean conditions, proper temperature control, regular maintenance schedules. He pointed to the Siemens motor's gleaming steel bearings. "These bearings will operate for 10,000 hours under correct conditions." "That's the problem," Manning said, pulling out a bearing from Sprague's motor. The bronze sleeve looked crude compared to Steinmetz's precision steel, but Manning's trained eye saw different virtues. "This bronze bearing has 500% load safety margin. When your tight tolerances expand from heat, our loose tolerances compensate. When dirt gets in, bronze absorbs it. Steel chips and fails. The test parameters reflected the brutal reality of American industrial conditions. Both motors would power identical rolling mills at the Carnegie Steel plant, operating 16 hours daily in temperatures ranging from 20 degrees below zero during Pittsburgh winters to 120 degrees beside the furnaces. Coal dust would coat everything. Maintenance would happen during brief Sunday shutdowns, if at all. Thomas Morrison, the Carnegie plant manager, had seen too many elegant European machines fail under such conditions. European motors assume perfection, Morrison told the assembled engineers, his voice carrying the authority of 15 years managing steel production. My job is making steel when conditions aren't perfect, when bearings can't be cleaned daily, when temperatures swing faster than maintenance schedules. He had watched beautiful German machinery seize up during critical production runs, costing thousands in lost output, while crude American equipment kept running. Steinmetz defended his position with characteristic precision. German engineering eliminates variables through scientific method. We calculate exact specifications, then manufacture to those specifications exactly. American tendency toward oversizing wastes material and energy. Our motor produces equivalent power at 63% the weight. But Sprague had spent months analyzing motor failures in American factories. European precision collapsed when reality deviated from specifications. Carl, your motor is engineered perfectly for German conditions, but American factories operate in chaos. Temperature variations that would shut down German plants, dust levels that would horrify German inspectors, maintenance schedules that exist only on paper. He opened the casing of his motor, revealing the massive cast iron frame. This isn't waste, it's thermal mass that absorbs temperature shocks your steel frame can't handle. Manning supported Sprague's philosophy with practical experience. Bronze bearings cost more than steel, but they last longer under abuse. Our commutator has twice the copper content because arc damage is inevitable here. European motors optimize for ideal conditions. We optimize for survival. The conversation revealed the fundamental divide between European and American engineering philosophy. Steinmetz represented centuries of guild tradition that achieved perfection through controlling variables. Sprague embodied American pragmatism that assumed variables couldn't be controlled, so equipment must accommodate chaos. The weight difference between their motors symbolized this philosophical gap: German precision versus American durability. As November faded into December, both motors shipped to the Carnegie plant for installation. Steinmetz remained confident his superior engineering would triumph over American crude oversizing. Mathematical precision had never failed him. But deep in Pittsburgh's steel mills, conditions existed that no German textbook had ever described. And the true test of motor philosophy was about to begin under the unforgiving demands of American industrial reality. Walter Manning stood before the foundry foreman at Pittsburgh Iron Works, sketching calculations on the back of a work order as molten iron glowed orange in the furnace beyond. The foundry's heat made sweat bead on his forehead, but his pencil moved steadily across the paper, defining what would become known as the Pittsburgh Principle. Every component gets sized 40% above calculated requirements, he explained to the burly Irishman who would supervise the casting. Frame thickness, bearing journals, armature shaft diameter, 40% over European specifications. The foreman, Patrick O'Malley, had cast engine blocks for steamships and locomotive frames that absorbed punishment no European workshop could imagine. He studied Manning's sketches with approval. Aye, that's railroad thinking. Build it stronger than it needs to be because it'll face worse than you expect. His crews had learned this principle casting components for the Pennsylvania Railroad, where equipment failure meant derailments and deaths. Sprague's motor frame required 127 pounds of cast iron, poured into sand molds that created walls twice as thick as German specifications demanded. The mathematical logic was simple but revolutionary. Where European engineers calculated exact stress requirements, then built precisely to those limits, American engineers calculated requirements, then added massive safety margins. The extra weight wasn't waste, it was insurance against the unpredictable violence of industrial operation. Manning supervised each casting personally, measuring frame wall thickness with calipers as the iron cooled. German frames used quarter-inch walls calculated to handle specific loads. American frames used 3/8-inch walls capable of handling loads that would never occur under normal operation. Cast iron absorbs vibration that destroys precision steel, Manning explained to his apprentice machinist, a young German immigrant named Hans Weber who struggled to understand American methods. Your homeland builds for perfection. We build for chaos. The bearing design represented the clearest departure from European philosophy. Steinmetz's steel bearings achieved their precision through manufacturing tolerances that required specialized grinding equipment and constant lubrication. Manning's bronze sleeve bearings deliberately incorporated clearances that German engineers considered sloppy workmanship. Where German bearings fit with 5/10,000ths clearance, American bearings allowed 1,000th, 20 times looser by European standards. Weber questioned this approach during machining operations. Herr Manning, these tolerances will cause vibration. German bearings eliminate play for smooth operation. His training at Krupp Steel had emphasized precision fits that eliminated mechanical slack. The American approach seemed to abandon everything he had learned about quality manufacturing. Hans, tight tolerances work in controlled conditions, Manning replied, showing the young machinist a failed German bearing from a local steel mill. The precision steel had chipped and scored when coal dust penetrated its microscopic clearances. But when temperature rises 50 degrees, metal expands. When dust gets in tight clearances, precision becomes destruction. He demonstrated with bronze and steel samples, showing how bronze absorbed foreign particles while steel fractured under the same contamination. The commutator design embodied American durability philosophy most dramatically. German commutators used minimal copper content, relying on precise manufacturing to prevent arcing that wasted material. American commutators doubled the copper thickness, accepting that arcing was inevitable in industrial environments. Where German designs prevented problems through precision, American designs absorbed problems through massive overspecification. Sprague worked 18-hour days throughout the winter of 1895, personally inspecting every component as his team developed manufacturing techniques that European workshops had never required. American foundries learned to pour thicker castings without creating internal flaws. American machinists learned to work looser tolerances that still maintained functional accuracy. Most importantly, American engineers learned to think systematically about equipment survival rather than equipment optimization. The philosophical breakthrough came during a February meeting when Thomas Morrison visited the Westinghouse plant to inspect both motor designs before installation. The Carnegie manager hefted Sprague's motor with obvious satisfaction. "This feels like equipment that won't quit on me during a critical pour," he said, comparing it to the elegant Siemens unit. "German motor looks like jewelry. American motor looks like it belongs in my plant." Manning explained the thermal dynamics that made weight advantageous rather than wasteful. Cast iron mass absorbs temperature spikes that would expand German steel frames beyond bearing tolerances. When our furnace kicks in, an ambient temperature jumps 40 degrees in 10 minutes. This thermal mass keeps bearing clearances stable. German precision can't compensate for American temperature chaos. The bearing metallurgy represented months of experimentation with bronze alloys that combined durability with self-lubrication properties. American foundries developed bronze compositions that embedded graphite particles for natural lubrication, reducing dependency on maintenance that German bearings required, but American factories couldn't provide. The result was bearing systems that actually improved with use, as embedded lubricants created protective films that prevented wear. By spring 1896, Sprague's team had created motor manufacturing techniques that challenged fundamental assumptions about engineering efficiency. European workshops achieved optimization through controlling variables, temperature, cleanliness, maintenance schedules, operator training. American workshops achieved reliability by designing components that functioned regardless of variable control. The weight penalty was acceptable because American industry prioritized uptime over theoretical efficiency. The completed motors embodied completely different engineering philosophies. Steinmetz's Siemens motor represented mathematical perfection, every ounce serving calculated purpose, every tolerance optimized for ideal performance. Sprague's American motor represented pragmatic durability, every component oversized for survival, every tolerance loosened for accommodation of real-world chaos. The Carnegie Steel plant would soon determine which philosophy better served American industrial demands. But the manufacturing process had already demonstrated that American engineering was developing its own sophisticated approach to mechanical reliability through systematic overbuilding rather than precision optimization. Thomas Morrison arrived at the Carnegie Steel plant before dawn on October 15, 1896, carrying his leather logbook and a brass pocket watch that would time the most crucial industrial experiment in American manufacturing history. The autumn air carried the metallic bite of approaching winter, and Morrison knew the temperature variations ahead would test both motor designs beyond any European laboratory simulation. He had positioned the two motors on identical rolling mill stations, each driving the same load under identical conditions that would reveal which engineering philosophy could survive American industrial reality. The installation had required precise calibration to ensure fair comparison. Both motors connected to rolling mills processing identical steel billets through the same reduction sequence. Morrison's engineers had matched electrical loads, mechanical couplings, and operational parameters so that only the fundamental design differences would determine performance. The German Siemens motor hummed with mechanical precision, its steel bearings operating at exactly 1200 RPM with minimal vibration. Sprague's American motor ran at the same speed but with the deeper rumble of heavier construction, its cast iron frame absorbing operational stresses that transmitted through the German unit's lighter structure. Karl Steinmetz visited monthly during the first 6 months, recording performance data with characteristic German thoroughness. His logbook documented operational hours, bearing temperatures, vibration measurements, and power consumption with scientific precision. The Siemens motor performed flawlessly through the mild months, validating European engineering assumptions about controlled industrial environments. Precision engineering delivers predictable results, Steinmetz told Morrison during his March visit, pointing to data showing consistent performance across all measured parameters. But Morrison noticed subtleties that Steinmetz's instruments couldn't measure. The German motor's steel bearings required daily lubrication to maintain their tight tolerances, a maintenance schedule that worked well during normal operations, but became problematic during the intense production periods that characterized American steel manufacturing. When Carnegie pushed for maximum output during spring construction season, maintenance windows disappeared, and the Siemens motor began showing stress indicators that Morrison's experienced ear detected before instruments registered problems. Walter Manning arrived for monthly bearing inspections, bringing specialized tools to measure wear patterns and clearance changes that revealed each motor's response to accumulated stress. The American motor's bronze bearings showed minimal wear after 6 months, with clearances remaining within acceptable ranges despite irregular lubrication. The German motor's precision steel bearings maintained their original clearances but showed microscopic scoring that indicated contamination problems. "Bronze accepts dirt and keeps running," Manning explained to Morrison. "Steel requires cleanliness or fails catastrophically." Summer brought the first serious test as Pennsylvania heat combined with furnace operations to create ambient temperatures that European motors had never been designed to handle. The rolling mill floor reached 105 degrees Fahrenheit during July heat waves, with localized temperatures near the furnaces exceeding 120 degrees. Morrison watched both motors carefully as thermal expansion began affecting bearing clearances in ways that separated robust design from precision optimization. The German motor began showing temperature sensitivity that Steinmetz's original calculations hadn't anticipated. Steel components expanded at different rates, creating internal stresses that tight tolerances couldn't accommodate. The precision bearings that operated perfectly at 70 degrees began binding at elevated temperatures, forcing reduced operating speeds that cut production efficiency. Morrison recorded these performance degradations in his daily logs, noting that the American motor maintained consistent operation regardless of temperature variations. Sprague visited during the hottest week of August, when ambient temperatures remained above 90 degrees for 6 consecutive days. His motor continued operating at full capacity while the German unit required speed reduction and additional cooling. Cast iron thermal mass moderates temperature swings, Sprague observed, placing his hand on both motor frames. The German motor's steel frame felt scorching to touch, while the American frame remained merely warm despite identical operating conditions. Weight becomes thermal stability when conditions exceed design parameters. The turning point came during the third week of September, when a critical steel order required continuous operation for 72 hours without maintenance breaks. Morrison had faced similar production emergencies before, knowing that motor reliability during peak demand determined whether Carnegie met delivery commitments or lost major contracts. Both motors began the marathon run in good condition, but the stress of continuous operation without lubrication quickly revealed the difference between precision engineering and survival engineering. The Siemens motor began overheating on the second day as its tight bearing tolerances demanded lubrication that production schedules couldn't provide. Steinmetz had designed his bearings for regular maintenance, assuming German factory conditions where production stopped for proper equipment care. American factories operated differently, expecting equipment to survive neglect during critical production periods. By hour 54, the German motor was running hot enough that Morrison could smell bearing lubricant breaking down. The catastrophic failure occurred at 11:30 a.m. on September 24th during a critical steel pour that required precise rolling mill timing. The Siemens motor's main bearing seized without warning, creating a mechanical lock that stopped the rolling mill instantly and ruined 3 tons of molten steel worth $4,000. The sudden stoppage damaged mill components, requiring 3 days of repairs that cost an additional $8,000 in lost production time. Morrison stood in the wreckage, calculating total losses of $12,000 from a single bearing failure. Sprague's motor continued operating throughout the crisis, its bronze bearings and oversized clearances accommodating the abuse that had destroyed the precision German unit. The American design's thermal mass and loose tolerances had absorbed stresses that exceeded the German motor's engineering margins, proving that survival required different design priorities than optimization. Morrison's final log entry for September documented the stark reality. American over-engineering had prevented a production disaster that European precision couldn't survive. The factory floor became quiet as word spread that the German motor had failed catastrophically while the American unit kept running. Workers who had initially mocked Sprague's crude-looking design now understood that industrial reliability required engineering philosophy that prioritized durability over elegance, survival over optimization. The telegram reached Frank Sprague at his Pittsburgh workshop on November 3, 1896, carrying news that would test American motor manufacturing more severely than any bearing failure. Silver panic spreads. Stop factory orders, canceled, stop banks calling loans, stop survival. Doubtful, read the message from his financial backer in New York. The economic depression that historians would later call the Panic of 1896 had arrived with devastating suddenness, threatening to destroy American motor manufacturing just as technical superiority had been proven. Sprague walked his factory floor that morning, counting machinery that might soon be auctioned to pay creditors. The casting equipment that had produced those revolutionary motor frames sat idle as orders evaporated. His workforce of skilled machinists and foundrymen faced unemployment as American factories shut down rather than invest in expensive domestic motors when European manufacturers offered desperate fire sale pricing to capture market share during the economic crisis. Walter Manning received similar devastating news at American Ball Bearing Company. European bearing manufacturers had flooded American markets with inventory sold at cost or below, making Manning's superior bronze bearings economically unviable despite their proven performance. Factory managers facing their own financial pressures chose immediate cost savings over long-term reliability, purchasing European components at 50% discounts that made American quality irrelevant to survival calculations. The financial pressure created impossible choices for American manufacturers. Thomas Morrison received authorization from Carnegie Steel to purchase replacement motors only if costs remained below emergency budgets that favored European suppliers offering distress pricing. Morrison understood the long-term implications, but faced immediate demands from company executives who prioritized quarterly survival over engineering philosophy. Buy the cheapest motors available, came the directive from Pittsburgh headquarters. We'll worry about reliability when we survive this depression. European manufacturers recognized their opportunity and responded aggressively. Siemens, AEG, and other German companies shipped inventory to American warehouses, offering motors at prices that undercut domestic production costs. Steinmetz found himself managing massive import operations designed to capture American market share while domestic competitors faced bankruptcy. The irony wasn't lost on him. Technical inferiority could triumph through economic warfare when superior American engineering couldn't compete on price. The collapse spread throughout American motor manufacturing with shocking speed. Westinghouse Electric reduced motor production by 70%, laying off engineers and machinists who had developed innovative manufacturing techniques. General Electric abandoned several experimental motor designs, focusing resources on electrical generation equipment that offered more reliable profit margins. Smaller manufacturers like Sprague Electric Motor Company faced complete closure as working capital disappeared and banks refused industrial loans. By December 1896, 3 major American motor manufacturers had declared bankruptcy. The Chicago Electric Motor Works sold its equipment to German competitors for 10 cents on the dollar. Boston Motor Company transferred its patents to Siemens for immediate cash that barely covered outstanding debts. The technical revolution that had proven American engineering superiority seemed destined to become a historical footnote as financial reality overwhelmed performance advantages. Sprague Electric Motor Company stock fell from $12 per share to $3 by January 1897, reflecting investor panic about American manufacturing's ability to compete globally. Shareholders demanded immediate cost reductions that would eliminate the over-engineering that made American motors superior but expensive. Board meetings became battles between financial survival and engineering integrity, with creditors threatening foreclosure unless production costs matched European pricing. The human cost was devastating for American workers who had developed revolutionary manufacturing techniques. Master foundrymen who could cast motor frames with precise wall thickness found themselves unemployed as factories closed. Skilled machinists who had learned to work with bronze bearings and oversized tolerances took jobs in other industries, dispersing knowledge that had taken years to develop. The brain drain threatened to eliminate American motor manufacturing capability even if economic conditions improved. Manning faced the cruelest irony, as factory managers who had witnessed his bearings outperform European alternatives now ordered European replacements due to financial constraints. "I know your bearings are better," Morrison told him during a painful January meeting, "but I can buy German bearings for 40% less, and my job depends on cutting costs immediately. Performance doesn't matter if we're bankrupt." European manufacturers pressed their advantage ruthlessly, offering maintenance contracts and spare parts support that made their low initial pricing even more attractive to desperate American factories. German engineers arrived to oversee installations, bringing technical expertise that American factories needed but couldn't afford from domestic suppliers. The temporary economic crisis was becoming permanent market displacement as European companies established distribution networks and service relationships that would survive economic recovery. The psychological impact on American engineers was profound. Sprague had spent 2 years proving that American over-engineering could outperform European precision, only to watch financial markets destroy that technical achievement overnight. The question haunting every American motor manufacturer was whether superior engineering meant anything if economic forces made it commercially irrelevant. Technical excellence seemed meaningless when customers chose inferior products based purely on price. By spring 1897, the American motor industry appeared finished. European manufacturers controlled 60% of the domestic market, with market share growing monthly as more American companies failed. The remaining domestic manufacturers survived by copying European designs and competing on price rather than performance, abandoning the over-engineering philosophy that had proven superior under real operating conditions. But deep in American factories, the motors installed during the previous years continued operating under conditions that would soon test European equipment beyond its design limits. The economic crisis had temporarily reversed the technical verdict, but the industrial proving ground would ultimately determine whether price or performance mattered more in American manufacturing. The Depression had created a vast, uncontrolled experiment that would settle the engineering philosophy debate once and for all, though the results wouldn't become clear until European motors faced the accumulated stress that American designs had been built to survive. Thomas Morrison entered his Carnegie Steel office on March 15, 1899, carrying a maintenance report that would vindicate everything Frank Sprague had believed about American engineering philosophy. The ledger documented 2.5 years of brutal industrial reality that had tested both motor designs under conditions no European laboratory had ever simulated. Morrison's weathered hands opened the book to pages that told the story of engineering philosophy, proven through accumulated punishment rather than theoretical calculation. The numbers revealed a pattern that had emerged gradually but undeniably. Sprague's 1896 motor had operated for 35,000 hours without major repair, surviving temperature extremes, contamination, and neglect that systematically destroyed European precision equipment. The original Siemens motor had lasted 8,000 hours before catastrophic bearing failure, followed by 3 replacement units that averaged similar lifespans before requiring complete rebuilds or disposal. Morrison walked the factory floor that morning, his experienced eye cataloging the evidence of durability triumph. The American motor still occupied its original position on rolling mill number 3, its cast iron frame now painted over multiple times but mechanically sound. Factory workers had grown accustomed to the steady rumble that indicated reliable operation, a mechanical heartbeat that never missed during critical production periods. The motor bore scars of industrial warfare, paint chipped by flying metal debris, housing dented by dropped tools, cooling fins caked with years of accumulated dust, but continued operating with the same steady reliability that had characterized its first day of service. The replacement European motors told a different story. Morrison examined the motor graveyard behind the maintenance shop, where failed German units awaited salvage or disposal. Steel frames had cracked under thermal stress that American cast iron absorbed without damage. Precision bearings had seized when contamination penetrated clearances that European engineers had optimized for laboratory conditions. Commutators had burned out under arcing conditions that American copper thickness had been designed to survive. Walter Manning arrived that morning to inspect bearing wear patterns that would document the mechanical superiority of over-engineering. His measuring instruments revealed the remarkable truth about bronze bearing performance under extended abuse. The American motor's bearings showed wear consistent with normal operation, despite years of irregular maintenance and contamination that had destroyed multiple sets of German bearings. The bronze had developed protective patinas that actually improved lubrication properties over time, creating self-maintaining systems that precision steel bearings couldn't match. European bearings optimize for ideal conditions that don't exist in American factories, Manning explained to Morrison as they examined failed German components. Our bearings accommodate reality. Bronze absorbs contamination and keeps running. Steel requires perfection or fails completely. His measurements documented clearance changes that remained within acceptable tolerances for the American design, while German replacements had exceeded specification limits before failure. The economic vindication was equally compelling. Morrison's cost analysis revealed that the higher initial price of American motors had been recovered through reduced replacement and maintenance expenses. The Carnegie plant had spent $6,000 replacing European motors over 2 years, while the single American motor required only routine lubrication and brush replacement costing less than $200. The total cost of ownership strongly favored American over-engineering despite the premium initial investment. Frank Sprague received Morrison's report by mail in his New York office, where he had relocated after the economic depression forced closure of his Pittsburgh manufacturing operation. The vindication came too late to save his company, but validated every principle he had fought to establish. American engineering could create superior industrial equipment through systematic overbuilding that accommodated real operating conditions rather than theoretical optimums. The weight penalty that European engineers had criticized as crude inefficiency had proven essential for survival under American industrial demands. The testimony Morrison prepared for the American Society of Mechanical Engineers documented the most comprehensive motor durability comparison in industrial history. The Sprague motor installed in 1896 continues operating after 35,000 hours of service, Morrison wrote. We have replaced the German equivalent 4 times, with average service life of 8,000 hours per unit. American over-engineering has proven its superiority through accumulated performance data that no laboratory test could simulate. Carl Steinmetz read Morrison's testimony with the intellectual honesty that characterized his scientific training. The data was indisputable, despite conflicting with everything his German education had taught about engineering efficiency. European precision had failed under conditions that American crude overbuilding had survived effortlessly. The mathematical beauty of optimized design meant nothing if operating conditions exceeded optimization parameters more often than design assumptions predicted. By 1900, the industrial verdict had spread throughout American manufacturing. Factory managers who had initially chosen European motors based on price and elegance now demanded American-built replacements that could survive real operating conditions. The economic depression had temporarily favored European imports, but the accumulated maintenance costs and replacement expenses had reversed the financial equation. American over-engineering cost more initially, but delivered lower total ownership costs through superior durability. The philosophical transformation extended beyond motor manufacturing to American industrial design generally. General Electric adopted overbuilding standards based on Carnegie's motor experience. Westinghouse incorporated durability margins that European competitors considered wasteful, but American factories demanded for reliable operation. The Sprague standard became industry practice. Overrate components by significant margins, use materials that accommodated abuse rather than optimized performance, and design for survival rather than theoretical efficiency. Morrison stood before the original Sprague motor on December 31, 1900, calculating 4 years of continuous service that had validated American engineering philosophy through the most rigorous testing possible. The motor's cast iron frame remained solid, its bronze bearings continued operating within specification, and its oversized commutator showed wear patterns consistent with decades of additional service life. European precision had proven beautiful but fragile, while American over-engineering had demonstrated the industrial virtue of crude reliability that refused to quit under any circumstances. The weight that European engineers had criticized as primitive inefficiency had become the foundation of American industrial supremacy, proving that durability trumped optimization when conditions demanded equipment that simply would not fail.